So we ended Wednesday at the bottom of page 1, right? We learned how to create a new function from two other functions by adding the two functions, subtracting the two functions, multiplying the two functions, and dividing the two functions, and how to find the domain of the new function. Okay? So if you flip over your page to the top of page 2, we're still continuing with example 1 on the previous page. We have to evaluate f plus g of 5. Okay. So to find the new function f plus g, right, we add f of x and g of x. But in this case, we're evaluating the function f plus g at x equals 5. So this is equal to f of 5 plus g of 5. Well, from the previous page, f of x is equal to 1 over x plus 3. So f of 5 is 1 over 5 plus 3. And g of x from the previous page is equal to x over the square root of x plus 4. So g of 5 is equal to 5 over the square root of 5 plus 4. Now it's arithmetic, right? First quotient is equal to 1/8, and the second quotient, the denominator here, right? Under the square root, 5 plus 4 is 9. Square root of 9 is 3. So this is equal to 5/3. And now you're just adding two fractions. And when you add two fractions, you need a common denominator. And the common denominator in this case is 3 times 8, which is 24. So we multiply the top and bottom of the first fraction by 3. We have 3 24ths. We multiply the top and bottom of the second fraction by 8. We have 40 24ths. And 3 24ths plus 40 24ths is 43 24ths. All right. And then next we have to evaluate fg of 0. Fg at x equals 0. Well, that's equal to f of 0 times g of 0. To get the function fg, right, we multiply f of x and g of x. Well, f of 0 is 1 over 0 plus 3. And g of 0 is 0 over the square root of 0 plus 4. 0 plus 3 is 3. So the first fraction is 1/3. But the second denominator under the square root, 0 plus 4 is 4, and square root of 4 is 2. But then we have 0 divided by 2, which is just 0. So this thing just equals 0. Any questions on that? Okay. All right, example 2, we have a word problem. common air pollutant responsible for acid rain is sulfur dioxide, SO2. Emissions of SO2 from burning coal during year X are computed by f of x in the table. Right? So X is the year. So this is year 1860, year 1900, year 1940, and so forth. Okay. And the emissions of SO2 from burning coal during that year are given by f of x. So here's f of x. So amounts are in millions of tons. So 2.4 million tons of SO2, right, were emitted in 1860, and 55 million tons of SO2 were emitted in the year 2000. Okay. That was from burning coal. The SO2 from burning oil are given by G of x. So the amount of SO2 from burning oil in 1860 was 0 million tons, and the amount of SO2 emitted in 1970 from burning oil was 17.6 million tons. Okay. Estimate F plus G of 1970 and interpret your answer. So F plus G evaluated at x equals 1970, right, adding two functions. So this is F of 1970 plus G of 1970. And F of 1970, that's the amount of SO2 emissions from burning coal. That was 32.4 million tons. G of 1970, that's equal to 17.6, right? That's the millions of tons of SO2 emitted from burning oil. And the sum of those two numbers is equal to 50. Okay. And now, right, this is where you gotta have the units, right, in order for this to make sense. This is equal to 50 million tons of SO2 were emitted from burning oil maybe I should put them in sequence. From burning coal and burning oil in 1970. So we evaluate F plus G of 1970, and that's the interpretation. F plus G of 1970 is equal to 50 million of the interpretation, 50 million tons of SO2 were emitted from burning coal and burning oil in 1970. Any questions on that? All right, so now let's talk about composition of functions, composition of two functions. So F and G, that F and G be functions where the range of G is in the domain of F. And I remember composition of functions being on my ACT math test when I took it as a senior in high school. So I'm presuming that everybody in here had some exposure to this in high school algebra. And if you take college algebra here at the College of Charleston, you definitely had exposure to it. So, the composition of the function f with g is denoted with its notation. This is the composition with the function g as a function of x. This open circle here is not a multiplication symbol. It's what we call a composite operator. It means you're taking the composite of the function f with the function g. And by definition, this is equal to f of g of x. This is read f of g of x. So, g of x is called the inner function because it's inside the function f of x. F of x is called the outer function because it's called the inner function because it contains g of x inner function. If you guys got to take Calc 1, it's important that you understand composite functions because we're doing differentiation of functions in calculus right now, and one type of function we have to be able to differentiate is a composite function. And we'll be talking about differentiation here in the not too distant future here in this class, just to give you an introduction to it. All right. So in example 3, you're given two functions, f of x and g of x. And we got to find the following for those two functions, f of x and g of x. So f of x is equal to 2 over x plus 3, and g of x is equal to 5 minus x. So in A, we have to find a composite of f with g as a function of x, okay? So by definition, that's equal to f of g of x. Okay. Well, the first step is to replace g of x with what it's equal to. Well, what's g of x equal to? It's equal to 5 minus x. So this is equal to f of 5 minus x. Now you have to evaluate the function f at 5 minus x. How do you do that? You put 5 minus x in for x in f of x. So you evaluate the function f at 5 minus x. Wherever you see an x on the right hand side, put 5 minus x. So this is equal to 2 over 5 minus x plus 3. I just replace the x here with 5 minus x. And now when we simplify the denominator simplifies 8 minus x. So the composite of f with g as a function of x is equal to 2 over 8 minus x. Any questions on that? Okay, and B, we gotta reverse the order of composition. And when you reverse the order of composition, you don't get the same function. Okay? So the order of composition matters. And so by definition, this is equal to G of f of x. And so the first step is to replace, right, f of x is the inner function now. And the first step is to replace f of x with what it's equal to. Well, it's equal to 2 over x plus 3. So this is equal to G of 2 over x plus 3. And now to evaluate G of 2 over x plus 3, wherever we see an x on the right hand side of G of x, we put in 2 over x plus 3. So this is equal to 5 minus 2 over x plus 3. And now you got to simplify, right? And so the common denominator here is x plus 3, right? This difference. So we're going to multiply 5, top and bottom, by x plus 3. So 5 is equal to 5 over 1. And then we're going to multiply top and bottom of that by x plus 3. And so we end up with 5 times x plus 3 over x plus 3 minus 2 over x plus 3. And now we got the difference of two fractions or two quotients with the same denominator, so we can combine the numerators. We have 5 times x plus 3 minus 2 over x plus 3. Now you distribute the 5 inside the parentheses. You have 5x plus 15 minus 2. And now the numerator simplifies to 5x plus 13. That's all over x plus 3. Now we're done simplifying. So the composite of G with f as a function of x is it simplifies to 5x plus 13 over x plus 3. Now I threw a lot of steps in there, and I know a lot of you can do jump a couple steps, right? All right. In C, we're going to take the composite of a function with itself. You can do that. So in C, we have the composite of the function f with itself. So this is equal to f of x. Right. You see the G here? Replace it with f. And so we just end up with f of x. So step number 1, replace the inner f of x with what it's equal to. So this is equal to f of 2 over x plus 3. And now we replace the x, right, and evaluate f of 2 over x plus 3. We replace the x here on the right hand side of f of x with 2 over x plus 3. So this is equal to, we're going to have a complex fraction, 2 over x plus 3 plus 3. All I did was replace this x right here with 2 over x plus 3. Now that's a complex fraction, right? We got a fraction inside a fraction, so we got to simplify, right? So this is the main denominator. So we're adding these two numbers, or this fraction, to 3, and x plus 3 is the common denominator. So we got to multiply top and bottom of 3 by x plus 3. So this is equal to 2 over 2 over x plus 3 plus 3 times x plus 3 over x plus 3. Now in the main denominator, right, we're adding two quotients with the same denominator. So this is equal to 2 over 2 plus 3 times x plus 3 over x plus 3. Now, so this, right, we got this fraction in the main denominator. So we got to distribute the 3 inside the parentheses, and we get 3x plus 9. And so this part right here simplifies to 3x plus 9 over x plus 3. And 2 plus 3x plus 9 simplifies to 3x plus 11 over x plus 3. And so now we're dividing the number 2 by quotient, right? So we have 2 divided by, remember fraction bars are like division symbols. 2 divided by 3x plus 11 over x plus 3. Keep, switch, flip, right? Keep, switch, flip. So we keep the 2, change division to multiplication, flip the second fraction, right? Well, just so we do the multiplication correctly, just remember 2 is the same as 2 over 1. And when you multiply two quotients, you multiply straight across, right? So this is equal to 2 times x plus 3 over 3x plus 11. And you don't have to distribute it. Okay. Any questions on that? Yes?
If you distributed the 2, would it be wrong?
No. It's just not necessary. All right. So in D, we're doing something similar. We're taking the composite of the function g with itself. So in D, we have the composite of the function g with itself as a function of x. So by definition, this is equal to g of x. So step number 1, replace g of x with what it's equal to in the inside there, and it's equal to 5 minus x. So this is equal to g of 5 minus x. Now to evaluate g of 5 minus x, we just replace 5, or the x on the right hand side of g of x up here with 5 minus x. so this is equal to 5 minus, in parentheses, 5 minus x. Because we're subtracting that entire quantity, 5 minus x, not just the positive. Now when you distribute the minus sign inside the parentheses, we have 5 minus 5 plus x, which is equal to x. So the composition of G with itself is just equal to x. Okay. Any questions on this thus far? In E, we're going to take the composite of f with G and evaluate it at x equals 2. Okay. So we're evaluating the composite function at a specific value of x. Okay. Now there are two approaches to do this. In A, we found the composite of f with G as a function of x, right? So we could use the result from A and just put 2 in for x. It'll result in A, right? In A, that is equal to 2 over 8 minus x. Okay? So I'm going to show you two different ways to do this one. Okay? Let's do what might be the traditional way. Is by definition, this is f of G of 2, right? And so the first step is to evaluate G of 2. Well, G of 2, from our function up here, right, you just put 2 in for x. On the right hand side, we have G of 2 is equal to 5 minus 2, which is equal to 3. So G of 2 is equal to 3. So we replace G of 2 with 3. And so this is equal to f of 3. Okay. And now to evaluate f of 3, put 3 in for x. And f of x on the right hand side. And we have 2 over 3 plus 3, which is equal to 2 6, which is equal to 1/3. Alternatively, if we had used the result from A, we could put 2 in for x. We had the composite of f with G at x equals 2 is equal to 2 over 8 minus 2, which is equal to 2 over 6, which is equal to 1/3. They both give you the same answer, and they're better. If you get two different answers, you did something wrong somewhere. Okay. So in this case, since we already knew what the composite f of G as a function of x is, we could have used the result from A, or we could have used a traditional way of evaluating that composite at x equals 2. Okay. Both ways work. Okay. All right. So any questions on example 3? Well, in example 4, we're taking the composite of 3 functions. We don't have to limit ourselves to just 2. So we have f of x is equal to x squared minus x. We have g of x is equal to 3x plus 5. And h of x is equal to the square root of x minus 3. So you got to find and simplify f of g of h of x. So h of x is the inner function to g, and g of h of x is the inner function to f. Okay. And often in the calculus, right, we're differentiating stuff like this. For those of you who have to take Calc 1. Okay. All right. So, but in evaluating this, the process is the same as with just two functions, right? The innermost function, in this case h of x, you replace it with what it's equal to. Okay? And it's equal to the square root of x minus 3. So this is equal to f of g of square root of x minus 3. Okay. So now we got to evaluate g of x minus 3. Right? So to do that, you just replace the x on the right-hand side of g of x with that square root of x minus 3. Right? So g of square root of x minus 3 is equal to 3 times the square root of x minus 3 plus 5. So g of square root of x minus 3 is the inner function to the function f. So to evaluate g of square root of x minus 3, we just replace square root of x minus 3. We just replace x up here to square root of x minus 3. So g of square root of x minus 3 is equal to 3 times the square root of x minus 3 plus 5. Now we have to evaluate f of 3 times the square root of x minus 3 plus 5. How do we do that? We replace each x on the right-hand side of f of x with 3 times the square root of x minus 3 plus 5. And then we got to simplify that. Okay. So this is equal to 3 times the square root of x minus 3 plus 5 squared minus, in parentheses, 3 times the square root of x minus 3 plus 5. Does that look like a lot of fun to simplify? Not really, right? So, over here on the side, three times the square root of x minus 3 plus 5 squared, you know it's just 3 times the square root of x minus 3 plus 5 times itself, right? So when we FOIL, we got to multiply first terms, right? To multiply first terms, we have 3 times 3 is 9. And square root of x minus 3 times square root of x minus 3 is just x minus 3. Right? So when we multiply first terms, we have 9 times x minus 3. When we multiply outer terms, we have 5 times 3 times the square root of x minus 3. 5 times 3 is 15, so we have 15 times the square root of x minus 3. Right, that's the outer terms multiplied. And then when we multiply the inner terms, we get the same thing. 5 times 3 times the square root of x minus 3. So we have plus 15 times the square root of x minus 3. And then when we multiply last terms, we have 5 times 5, which is 25. Okay? And then We have minus this in parentheses, so we gotta distribute the minus sign. When you should minus, we have minus 3 times the square root of x minus 3 minus 15. No, where did I get the minus 15? It's minus 5. We're just changing the sign of each term inside the parentheses. Alright. And now we combine like terms. Okay? We only have one term involving x minus 3. 9 times x minus 3. But we have 3 terms involving square root of x minus 3, right? 15 plus 15 is 30, and 30 minus 3 is 27. So we have plus 27 times the square root of x minus 3. And then we have plus 25 minus 5, which is plus 20. And that's where I stopped with the simplification. If you wanted to, you could distribute the 9. You have 9x minus 27. Then add minus 27 and 20. Right? But I stopped right there. Any questions on that?